open and closed sets are almost the same as the open and closed sets that we learned in chapter 2. The only difference is, instead of the absolute value, we are going to have the distance function. So before we define open set, we want to define something similar to an open interval. Now in a metric space, we call this an open sphere, or the open ball. So first we'll define an open ball or the open sphere. So we start with a metric space. So I take xd to be a metric space, and I take a fixed point a in x and a number that is greater than 0. The open ball of radius r centered at A is the set. Now when we write, we can write this one as B d A r, where x in x such that the distance from A to x is strictly less than r. Now if your metric is clear, we just write B A r, or sometimes you can just write B A, instead of a colon we can just put a comma. But when you sometimes work with two metrics, we want to write D as a sub, or we want to index by D because we are not sure which metric we are working with. So it comes with the context. And similarly, we can define the closed ball to be, so we can use the closed interval thing, like a close brackets AR, to be all the elements x in x such that the distance between A to x is less than or equal to r. So this is something like the open ball. So I have a point A, and all the points that are within distance r to this point. And it's very important to note that an open ball might not be a ball or a sphere. So it might not be, I just use the word circular. It might not be in a circular shape like a sphere. It can be anything depending on how you define a metric. So we look at some example, the standard 3 examples. So the first example is, if you go back to chapter 2, we have the set of real line with the absolute value metric. Then we know that the open ball, say x r, is the open interval. So I have the fixed point x and x minus r and x plus r. So this is an open interval. And the second example, I'm going to take r squared and a Euclidean metric. The distance is measured by x1 minus y1 squared plus x2 minus y2 squared, and then you take the square root. So I'm looking at the open ball, say the open ball centered at say the origin and the radius 1. So if I write this, so I want to look at all the points xy in R squared such that the distance between xy and the origin is less than or equal to 1. Now the distance is measured using this formula. So I have all xy in R squared such that square root of x minus 0 squared plus y minus 0 squared is strictly less than 1. So this means all the elements xy in R squared such that x squared plus y squared is less than 1, and you know that this is an open circle. So I have the origin, and I'm taking, and this is not the perfect way to do this, so okay. No, I think I need to do the dotted lines. And distance is 1. So that's the open ball centered at the origin with unit distance. Now the second example, we'll take the taxi cab metric in R squared. So if I define B01, so these are a set of points in R squared such that the summation of absolute value of xi minus yi is strictly less than 1. So I have xy in R squared such that, so my y coordinate is going to be the 0, so I have x minus 0 plus y minus 0 is strictly less than 1. And if we simplify a little bit further, I have absolute value of x plus absolute value of y is strictly less than 1. Now if I graph this set, so the absolute value should be, the sum of the absolute value should be less than 1. So for example, if I'm at -1 0 or 1 0, it's less than 1, so it should not include the points. And similarly, so it's going to be a diamond shaped, is it a rhombus, I think the word. So this is the open sphere centered at 0, so this is my 0 with distance or the radius 1. So it's not a ball. And the third example, we take the max metric. And if I look at the open ball, so I'm looking at the set of points x, y in R squared. Such that the distance, in this case it's going to be the maximum of x minus 0 and y minus 0 is less than 1. So the maximum of absolute value of x or y should be less than 1. Now if I graph the set, you will have the open square. So this is 1 1, this is minus 1 1, this is minus 1 minus 1, and this is 1 and negative 1. So it's a square.